So our first question here is talking about rocket fuel, hydrazine, which is one of the ones they quite like to use in exam questions because it kind of is just a neat little, not very large molecule. We can talk about bonding as well as energetics and principles from organic. So it tells us here that our hydrazine reacts with oxygen, and so it's a combustion reaction. We can see that it's exothermic, so of course, because it's a fuel, we want to give out heat, we want to create gaseous products at the volume of gas. That provides the thrust that actually pushes your rocket. So that's why it's a useful fuel. Now, the first part of the question they're asking us, what happens if hydrazine reacts with fluorine instead? So different reaction instead of oxygen. And it tells us it's all going to be a gas. So that's easy to put our state symbols in for an equation. So let's write the equation here. So we're still using, this is our hydrazine. We still have N2H4, and that's a gas. And instead, we would react with fluorine. Now, fluorine, you should know because it's a halogen, that it exists as a diatomic. It grows around in little pairs. And then that would create, you would still get nitrogen gas. You're effectively doing a very similar reaction here. Sorry, I told you I'm not very good with my stylus. And instead of water, you would have to get a compound with the remaining hydrogen and the fluorine here. So that would be just hydrogen fluoride, and that would be a gas. Now we need to balance that. There's 4 hydrogens here, and here we've got the wrong amount. Here we're going to have to balance as well. So let's just emphasize, should have left a bit more room. We will need 4 of those, because there are 4 hydrogens here, and then 4 fluorines. We need to have 2 fluorine gas molecules here as well. Okay, so there's our equation for our reaction for the first one. Now the next part tells us that we also should be able to draw a Lewis structure for them. So hydrazine is going to have nitrogen connected there, and then we've got our 4 hydrogens distributed around. So you could kind of, attempt to draw this in semi kind of tetrahedral way if you wanted to, but it doesn't really matter. The important thing to show here, sorry, my electrons aren't very nice there, is to make sure you have the correct number of electrons around your nitrogen. So here you want to show all our bonds with single lines is probably the best, but if you use dots or crosses, it's fine. And then these guys here, these lone pairs of electrons are really important because nitrogen has 5 electrons in its valence shell. So 1, 2, 3, 4, 5 around here. So making sure that lone pair is shown. So that's hydrazine. Let's draw, we'll just go to keep them color coded here. And then our nitrogen gas, that's a nice straightforward triple bond nitrogen. Again, still got those lone pairs. Okay, so that's our next part. Next thing we're going to use the average bond enthalpies given in table 11 of the data booklet to determine the enthalpy change for the reaction in part A. So part A is our reaction with our fluoride. So I'm going to, sorry, it's going to clash with my ink annotations a little bit, but just bring up those bond enthalpies. I'm sorry, I can't work out a way to cover what I've written with my pen there. But we have here, so if we've got, in fact, it's kind of useful because we can see here that we're going to have our hydrazine, which we've drawn. So we're going to have to break, in fact, we'll write the equation that the enthalpy change is equal to the sum of the energy of the bonds broken. I do find an old school whiteboard so much easier. Minus the sum of the energy of the bonds formed. All right, so we need to have then bonds broken. We're going to break this single nitrogen-nitrogen bond. So if I just kind of list them under here, nitrogen-nitrogen, got one of those. We've got nitrogen-hydrogen bonds. In fact, we've got 4 lots of those. So, and we don't forget that we're actually going to break the fluorine. So So there are also 2 fluorine covalent bonds there as well, because we're going to break apart that fluorine gas. And then the bonds formed, we're now going to make triple bond between our nitrogens, and we're going to make 4 hydrogen and fluorine bonds. So if I go back again, I'm just going to grab maybe slightly more distinct color. So if I tally those up, I've already highlighted them on that, just to make it a little bit easier. So if we look at our chart, nitrogen and nitrogen, that's our 158. Nitrogen and hydrogen together, it doesn't matter which way around you look it up in the table, you can go from along the top or down the side, doesn't matter which element you look up first, you'll get the same value. So nitrogen and hydrogen, we have 391, so we're going to need 4 lots of that. And fluorine, 159. And then, of course, our bonds formed. We go down the bottom to look for our multiple bonds. So our triple bonded nitrogen is 945. And 4 lots of hydrogen fluoride bonds here. So H and F, we have 5, 6, 7. All right, so if we tally those up, we should have on this side, bonds broken, 2040, and bonds formed, 3,213. So our delta H, it's broken minus formed, gives us, what does that give us? Gives us minus 1,173, and it's kilojoules, and it's per mole because it's per mole of hydrazine. So that's our answer to this question. I mean, it's important that we include that negative here, because it is an exothermic reaction. If we don't include that, you'll miss one of the marks. Okay, let me just get rid of that table again so you can see those answers without so much confusion. And then based on your answers to parts A and C, suggest whether a mixture of hydrazine and fluorine is a better rocket fuel than a mixture of hydrazine and oxygen. Well, we're basing that on the enthalpy values. So let's grab, so that's, I didn't mean to do a highlighter, but there are enthalpy values here for combustion. So you can see it's a lot higher when we react a mole of hydrazine with fluorine rather than a mole of hydrazine with oxygen. But it's still just 1 mole of each, so we can do a direct comparison. We can say that this is much more exothermic. You might also like to consider the fact that, so I'll just go to a pen instead, how much gas is produced. Because remember we said that it's the volume of gas that gives the rocket its thrust, that makes it move. Here we have 1 mole of nitrogen gas and 2 moles of water vapor, water gas. So we have 3 moles total of gas. Here we have 1 of nitrogen, we have 4 of hydrogen fluoride. And remembering back to our gas laws and stoichiometry, that the actual size of the molecule is pretty negligible, that actually it's just the number of moles of gas that give us our volume. So we have 5 moles of gas here. So this would be a greater volume. So that would propel our rocket better. So for 2 reasons, we can say the mixture of hydrazine with fluorine is a better fuel because it's more exothermic and there's a greater volume of gas to propel the rocket. Okay, that's question 21. Let's go ahead, just skipping a couple so we can get a bit of a spread of different skills. Let's go to question 23 now. I'm just going to go back to a friendlier colour. Okay, so 2 students are asked to use information from the data booklet to calculate a value for the enthalpy of hydrogenation of ethene to form ethane. So we've seen this when we've looked at organic, what that process is. Now we're looking at putting some energy values or enthalpy values with them as well. One thing to be mindful of, this question is from quite a few years ago now, where the data booklet values were slightly different. So if you do look up the actual mark scheme answers for this, they will be a tiny bit off. But if you're in the right ballpark, don't worry. It will just be reflective of the fact that the data booklet gets updated. Okay, so John used average bond enthalpies from table 11. That's one we looked at in the last question. And Marit used the values of enthalpies from combustion, which is table 13. So they're going to arrive at slightly different answers. Let's look at John's technique first. Calculate the value of enthalpy of hydrogenation of ethene using the average bond enthalpies in table 11. So again, we'll bring up that table 11 for a second. So again, I've highlighted them for you just because it gets a bit scribbly with the stylus. So a good thing too, if you can't remember, is probably to draw it. So here's ethane first of all, just in like a flat view there. So ethane, and we're going to have hydrogen gas, and we're going to make, oh, apologies, I'm going around the wrong way. We started with ethene, of course. How can we hydrogenate an alkane? That's interesting. So we've started with ethene, and we're getting ethane. My apologies, need more of that coffee. Okay, so hydrogenating our ethene to make ethane. So if we were looking at, again, that enthalpy change coming from the sum of the energy of the bonds broken minus the sum of the energy of the bonds formed, we should be able to calculate that for the overall reaction. So here, our bonds broken, we are breaking a carbon-carbon double bond. And we also, don't forget that our hydrogen gas, that's the thing that people are most likely to forget, the actual gas you're reacting it with. So we're breaking apart that diatomic hydrogen here. So there are our bonds broken. And then our bonds formed, we are making a new single carbon-carbon bond, and we are making two hydrogen-carbon, carbon-hydrogen bonds as well. So the two that we've added in. So just to highlight those in case you're a bit unclear, we are breaking that one and breaking that one. And we are forming these two and this carbon-carbon bond here that's only a single bond. Okay, so let's put those values in. So the double bonded carbon, we have 614, and the hydrogen is 436. And then we have our single bonded carbon is 346. So we can see that there's quite a difference there in the single and double bond. That double bond is almost twice as much as a single with our bond enthalpy, but not quite. And then what have we got? Carbon hydrogen. So we need two lots of 414. Okay, so our bonds broken, 1,050. Bonds formed, 1,174. So our enthalpy change should be minus 124 kilojoules. I think the marks here might have said 125, or maybe like might have been out one or two, just because again these values are averages and they're changed from year to year what data they're using, or they get refined a little bit over time. So that's answered our first question, so we can get rid of that. Now the second part, Mariette arranged the values she found into an energy cycle. I think the way this diagram is drawn is a little bit confusing just because there's such a big gap here. That's the equation we're looking for at the top, our ethene plus hydrogen becoming ethane. And table 13, by the way, and again, there'll be slight differences. Let me just bring that up for a minute. I really wish I could do that over the incantations. So these are the enthalpies of combustion. You can what she's done is she's taken here this ethene, which, apologies, is now scribbled over. But looking at the enthalpy of combustion, what would happen if you reacted that with oxygen? So with 3 moles of oxygen, you would get 2 moles of carbon dioxide. You actually wouldn't get that much water. You would only get 2 moles of water if you were to take ethene and oxygen. You would get the carbon dioxide and 2 moles of water, and that would be this value here. And then if you took the hydrogen, and the hydrogen's in the table as well, hydrogen with half a mole of oxygen, you would get our other mole of water here. That's why we get a total of 3, and that would be this value. So what we can say is kind of this whole thing combined, that here, if we combust both ethene and hydrogen at the same time, we should be able to add these values together. So what's that? We would get minus 1,697 kilojoules per mole. Or it's getting pretty messy. Another way we might write that, I suppose, if we wanted to rewrite this diagram, you might say C2H4 plus H2 goes to 2CO2 plus 3H2O, and that was minus 1,697. And we want to know to make ethane. Now this information here, we want to take that arrow and reverse it. So we're going to take that value and change the sign. So if we took that information, because the combustion information comes from that table as well, by combusting ethane, you get carbon dioxide and water, and that's the energy released, which is looked up from the table. So the reverse, to push it the other way, would be positive 1560 kilojoules per mole. I apologize, I've left the units off there. Okay, so now we have something we can work with. We can find out this one here by going along here. So hopefully you guys are with me there, that this part, the combustion data for ethene and for hydrogen gas can be combined in order to find out what this bit is together. So that was this information gave us this one here, looking up the individual values for those two. So the combustion of the two of them together gives us that value, and then we can use that information and that information by reversing the sign to get to the value of the conversion of ethene and hydrogen to ethane. So now we just add those two together. So negative 1,697 plus positive 1,560, we get a value of, oh, I'm in highlighter mode, sorry. Gives us a value of minus 100 oh, now I've done it, haven't I? Minus 137 kilojoules per mole. And that's our answer to that question. So that's using that energy cycle diagram and using the enthalpy values of combustion from table 13. So both of them were trying to arrive at the same answer, and they've got slightly different things here. So we've got John's answer by using bond enthalpy values, which is, again, the wonders of my stylus, and that's just 100 minus 137, and I've accidentally just turned it into a highlighter writing. Okay, so we've got bond enthalpy values and we've got combustion values. Okay, let's go to the next part, and I'm obviously going to have to erase some things here because I've made it turn up on the next page. All right, which I cannot keep there. Oh dear. Okay, back to the pen. All right, so the next part of the question is to suggest why John's answer might be less accurate than Marit's. So we just mentioned then that John's answer was the one using bond enthalpies, and Marit's is from combustion. And just to save you the pain of my stylus writing, I've just decided to type that one in advance. So here's we're using average values. The range of compounds are used to calculate those average bond enthalpies. Whereas Marit's data, she used combustion data that was specific to the actual chemical compounds that are in this equation here. So hers is going to be more accurate because it's not affected by neighboring bonds or other interactions that might be happening in the range of molecules that the average bond enthalpy values come from. Okay, next part. John decided to determine the enthalpy of hydrogenation of cyclohexene to produce cyclohexane. All right, what are those compounds? Remembering that cyclohexene, it doesn't matter which one you pick. So let's put, say, the double bond there. So that's our cyclohexene over here. And if you wanted to make that cyclohexane, you would get rid of this. So you only have a single bond and you would hydrogenate it. You would put some hydrogen in. That's actually exactly the same as what we did in the last question. So you would break a carbon-carbon double bond and you would have to break some hydrogen gas. That's where the hydrogens came from. And you would form a new single carbon-carbon bond and two carbon-hydrogen bonds. So actually, if you use the bond enthalpy data, you would get an identical answer to the last question where we had ethane and ethene being hydrogenated to ethane. So that would give you, what was it? It was we calculated it to be minus 124 kilojoules per mole. It would be an identical answer. Doesn't matter about the rest of the molecule. Or does it? So that's if you use that data, but you'd imagine that actually the configuration of this molecule would have an effect. That's why those averages don't always give you the best answer. So that's our first part. And then this part here is kind of evaluating that a little bit, saying that the percentage difference in the two methods. So if you calculate the averages, or if you do it Marantz way using combustion, you get a bigger difference between the two values for this one, for cyclohexene, than you do for ethene. Why? Why might that be the case? Well, here's a clue here in our equation, is that we're actually, we've got these compounds in a liquid, whereas when we had ethene and ethane, they were gases. So there are intermolecular forces at play in a liquid. So the neighboring cyclohexene molecules, there are some interactions. And you would actually have to break those forces apart as well before you could, you know, if you were reacting it or if you were going to combust it, which would give you a bigger difference. So again, here's one I've prepared earlier for you. So ethene is a gas, no intermolecular forces. Cyclohexene is a liquid. So there is an enthalpy of vaporization that would also occur during combustion. So that's why there's a bigger difference. But if you use bond enthalpies and combustion data, the combustion data is there's going to be a greater difference for any chemical compounds that are in a solid or a liquid because they have intermolecular forces that have to also be overcome when you combust them. Okay. Last one to have a go at. And back to pen. All right, here's one where we're using a fuel and heating up some water. So a copper calorimeter, like this thing here. So you want to use something that actually is a good conductor for this, in this case, because your burner here, that's where you put your fuel. So we're using ethanol. So your ethanol goes into here and you weigh it before and after you use it. Then you light it and you heat a known mass of water so that you know you can do your calculation. You have a thermometer in here. Sometimes you might have a stirrer as well. Otherwise, you're assuming that it's the same temperature throughout, and it might not be. And then you've got other things to try to reduce heat loss around it as much as possible. But you want the heat to be transferred from the burner to the water. So you go for something that is a good conductor at the bottom. So the data we want to calculate the heat evolved from this one. So this is one of those Q equals M times C times W equations. So that's the heat evolved. We would use Q. We have to take into account how much water we've got. We also need to know the specific heat capacity, and we need to know how much the temperature has increased by. So that is, now we've used 100 mils of water, or centimeters cubed, which is 100 grams. We know the specific heat capacity is 4.18, or you can look it up in the data booklet if you need to. And then the temperature change, we do our final minus our initial. 55 subtract 20 is a 35-degree change. And that's to three significant figures there, one decimal place. Okay, so that gives us a value of, multiply that all together, we get 14,630 joules, or looks a bit neat if we want to make kilojoules, do 14.6, and actually stop at 6. As I said, there are three significant figures. So that's our heat evolved for that one. Now, the next part of the question is to make that, to calculate then what the enthalpy change of combustion was for the ethanol. So Q here was the heat exchanged in the water, and then the enthalpy change, kind of the context of what was happening in the fuel to make that happen. So first of all, we need to know how many moles of ethanol we actually burnt. So we know what mass we used is 1.78. And then ethanol, which, if you've forgotten, looks like this. So we have 2 carbons, 6 hydrogens, and 1 oxygen. So if we add those all up from the periodic table, we get a molar mass of 46.08 grams per mole. So the number of moles of ethanol is now 1.78 grams. And that was from the information given. Over 46. Oh, I've done it again. Do you have a crack in my laptop screen here? I'm sorry, which doesn't help, I think. Over our molar mass, and that tells us we have 0.0386 moles of ethanol that we burnt. So now we take our enthalpy of combustion is going to be the heat change that we calculated in the first part. Over the number of moles used. So that gives us an answer of minus, is exothermic, 378 kilojoules per mole. That is the enthalpy change of 1 mole of ethanol here. But of course, it's not going to be that accurate, and they're asking you to suggest some reasons why it wouldn't be the same as the value in the data booklet. Again, here's one I've done earlier. You can have quite a lot of heat loss to the surroundings, even if you're trying to block off some drafts. You are heating the surrounding air. You can have some heat then lost from warming up the actual copper calorimeter, or then from the calorimeter to the surrounds. Or you might find that actually if you don't have the correct ratio of oxygen in here, perhaps there was something that was blocking that you might have some incomplete combustion. So you might not be converting it all into carbon dioxide.